This video contains various seasonal characters. If you don't like Christmas mythology or logistic regression, you're probably not going to like it. There's some particularly awful singing because, like an idiot, I recorded the backing track without checking whether I could sing in the corresponding key. As it turns out, the answer was, I can't.
Now, boys and girls, I would like to begin with a Christmas tale. A tale of snow and frost and punishment. Now, as you know, I have two lists. Now, the first list is the nice list, and that's for all the good boys and girls, and it's a very, very long list. I'm happy to say that you're all on that list because you've been attending your lectures and working very, very hard. However, there is another list, a very, very sad list, a tragic list, you might say, and that is, of course, my naughty list. Now, the naughty list, as you may know, is for all the boys and girls who have misbehaved. Now, my attention was drawn recently to one particularly bad little boy. Tales got to me in Lapland that he'd been enticing young people with candy and hippopotami and all sorts of weird and wonderful things that made them think that they were going to do something very, very exciting, and then he got them all together, huddled around, watching. And when they least suspected it, he taught them statistics. Oh, what a naughty, naughty, naughty boy! Well, Santa thought to himself, I'm going to have to find out about this character. He sounds like a reprobate. So I travelled in my sleigh to the University of Sussex, and I found him in a little office, huddled in a corner, sad and alone with no friends whatsoever. Well, what I did was I took him back to Lapland. I thought, well, I could put him on my naughty list and then he wouldn't get any presents. But that seemed too good for him. Too very good for him. So instead, I thought I would unleash the Krampus upon him. Well, I don't know whether you have ever heard of the Krampus, but he's a sort of large half-goat, half-demon kind of anti-Santa. And what he does is he punishes the naughty by carrying them away in a sack or sometimes a wooden barrel and then giving them coal. And what's more un-Christmassy than getting coal instead of presents? But I thought coal seems like the perfect gift for this statistics chap. So anyway, I said to the Krampus, look at this chap over here. You can have him, put him in your barrel, take him away. I don't want him anymore. So the Krampus put him in his barrel and he carried him off. But as he did, I got a message from headquarters.
Santa, bad news! Bad news! We just got the reports back from last Christmas, and 10.6% of presents didn't get delivered!
What? How is that possible?
We don't know, Santa!
Oh, no. We can't have even a single present not being delivered, let alone 10 point whatever percent it was that you said. Whatever shall we do?
I don't know, Santa. There's no one to help us. All the elves are away with the fairies. Literally. It's the annual elf and fairy pre-Christmas holiday. If only there was somebody who could look at our data more thoroughly, a sort of statistics expert who could help us to find out which variables predict whether or not a present gets delivered.
Well, at this point, as you might imagine, Santa had a little bit of a panic. Ooh! As I was panicking, I noticed in the distance the Krampus disappearing with the little naughty boy from Sussex in his barrel. And just then, a little head popped out of that barrel, and it said to me,
Santa, I can help.
Very well. I said to the Krampus, unleash the human. Now, let me tell you, the Krampus wasn't very happy about this. But anyway, I got the human and he said to me,
Tell me about your operations.
well, I had this kind of small little hernia type thing once upon a time.
No, not those operations.
Oh, I see. Well, yes. Now, obviously, back in the day when there was only 3 humans on the planet, I used to deliver all the presents myself. But now, there's so many presents to deliver that I get the elves to help me.
And what happens during a delivery?
Well, generally one of us pops down a chimney or through a dog flap, or we sprinkle ourselves with magic Christmas dust and float through the letterbox as vaporous vapour things. And once inside, the kind people have usually left us some kind of little treat.
What kind of treat?
Nothing that would slow us down, just a little morsel of Christmas pudding or some mulled wine. Don't look at me like that, young man. Over many centuries I've evolved an incredible capacity for consuming mulled wine and Christmas pudding. I have, in fact, evolved a 4-dimensional stomach. I go into many houses, and it's very rude not to eat the treats that people leave, but where do you put it all? Well, the solution is evolve yourself a 4-dimensional stomach. It's a bit like Doctor Who's TARDIS, except that it's just as big on the outside as it is on the inside. Consequently, I'm completely impervious to the effects of mulled wine and Christmas pudding.
But what about the elves?
But then it hit me. Elves don't have 4-dimensional stomachs. Oh dear. But how could I find out if the treat consumption was in fact affecting the delivery of presents? So anyway, we struck a little deal. He would analyse my data for me on deliveries, and in return I would give him his freedom. But as he set to work, he made a little sad face at me, and he asked me for one final little Christmas wish. And I thought, well, I am Santa Claus, I suppose I could grant him one last wish, even though he is an extremely naughty boy.
Think of my children. I've taken them so far on their journey, so far down the road of the general linear model and R. They've worked so hard. They deserve a reward.
Well, I said, if you can save Christmas, I will release all of your students from the hell of this module and give them the best winter vacation ever!
Well, what a responsibility. I've got to save Christmas. Well, I think I'd better start like we've started every single lecture by thinking about how our model is going to fit in with the research process. So we've got a question to answer. Why is it that some of the presents don't get delivered? So we need to predict whether or not a present gets delivered. We're going to have to sample, get some data, which we already have, and then we'll visualize the data, we'll fit some kind of model to it, and then we'll have to check the assumptions of that model, etc. Now, the model we're fitting today is going to be slightly different to ones that we've looked at before, because our outcome is categorical, whether a present gets delivered or doesn't get delivered. But it's still essentially an extension of the general linear model. So we're still in this kind of part of the diagram. So the task that we've been set is to try and work out why presents don't get delivered. So our outcome is going to be whether a present gets delivered or not. And we're going to try and predict it from some things. And in particular, we're going to start off by looking at whether the treats that are left for the elves and for Santa at people's houses affect whether or not a present gets delivered. So we're just going to have a single predictor, which is whether the treat is Christmas pudding or mulled wine. Now the data looks like this. So we've got an ID variable that represents the elf that was doing the delivery. So we've got Fankle the determined, Amber the cuddle, Snorklam the content, Henry the biddable, etc. Ainsley the eigenvector, who is one of the more statistically minded elves. Then for each elf, we know which treat they consumed on their delivery, and we also know whether or not they delivered the present. So we know, for example, that Funnel Cup, the Iron Maiden fan, had some mulled wine and successfully delivered the presents. However, Bindlestiff the Surprised had some mulled wine and did not deliver his present. So this is what the data look like. And we got data from lots and lots of elves. We can go through all, oh my goodness me, look at all those elves. It's tons and tons and tons and tons and tons of them. 400 in fact. Okay, so Alexis the Spatch. Sorry, at some point in my life I made up 400 elf names to put in a data file. That's and I've forgotten some of them and they're making me laugh. Anyway, don't laugh at yourself, Andy, it's bad form. Anyway, so that's what the data looks like. If we were going to fit a standard linear model, the kind of model that we've been talking about all term, it would look something like this. So we'd be trying to predict delivered, so delivery. We'd have a single predictor of treat, and we know from previous lectures, because that's 2 categories, Christmas pudding or mulled wine, that we can put that into a linear model by using dummy coding. So we're going to code one of the categories with a 0 and one of the categories with a 1. For example, we might choose Christmas pudding as 0 and mulled wine as 1, but we could do it the other way around. We're going to have a parameter attached to treat that we're going to estimate, and this is going to represent the effect of treat on delivery. And we've got an intercept which represents the outcome, delivery, when treat is 0. So if we use the coding scheme on this slide, that means it will be the deliveries when Christmas pudding was the treat, because that Christmas pudding is coded as 0. So great, let's go do that. Except we can't, unfortunately, because it's going to violate the assumption of linearity. Now, way back, we had a whole lecture involving knights and wizards about the assumption of linearity and how important that was. And because our outcome is delivered or not delivered, this assumption is violated. And it's a very important assumption. If you're going to fit a linear model, you kind of need the relationship that you're modeling to be linear. In this case, it's not going to be, because we've got a categorical outcome. So we can't fit this model. But we can fit something very similar. So because we can't fit a standard linear model, because we're going to violate the assumption of linearity, what we can do is basically reconstruct the model in a form where it retains the linear model that we know and love, but it has a kind of a different form to it to deal with the fact that we have a categorical outcome. And one way to do this, there's actually 2 ways of expressing the equation on this slide. On the next slide, I'm going to show you a different way of expressing it. They're identical. They're just a mathematical rearrangement of the same equation. You can actually go through and rearrange it, and they are the same. But I'm going to explain it both ways, because some ways make more sense to some people than others. So the first way is to express our outcome not as the outcome itself, but as the probability of the outcome. So the probability of a delivery or not being delivered. And by expressing the kind of linear model in this form, we end up with the outcome being the predicted probability that delivery will occur. And that is predicted from 1 over 1 plus e to the power of minus beta 0 plus beta 1 x1 blah 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 blah. Now the thing to note here is our standard linear model with the intercept, the predictor variable, and the parameter associated with the predictor variable. That standard model is in this equation, so it's still there. The thing we've been doing all term is still there. It's just tucked away in a sort of re-expression of or in a re-expressed form. So the linear model is still there, it's just expressed differently, so our outcome has become the probability of a delivery occurring. Now, as I said, there's a different way to express the same thing, which is like this, and people, I think, maybe find this a bit easier in general. If you rearrange the equation on the previous slide, you end up with this. So like I said, it's exactly the same equation, it's literally rearranged. So it's a rearrangement of the equation on the other page. And in doing it like this, what we end up with is, on the right hand side, we have the natural logarithm of this fraction. So the probability of delivery over 1 minus the probability of delivery. So essentially what that is the probability of delivery over the probability of non-delivery. And then that's expressed in natural log units. And then on the right hand side of the equation we have our standard linear model. So basically you can think of it as the same as the linear model that we've been using all throughout this module. It's just when we have a categorical outcome, the left hand side changes. So what we're predicting changes. Instead of predicting delivered or not delivered, we predict some function of the probability of being delivered, and that allows us to still use this kind of linear form of the model. Now, of course, the problem with this is we understand very well what's going on the right hand side. We've been doing that all term long, so hopefully we've got a fairly good grasp of what's going on the right hand side of that equation. Stuff on the left, not so much. That's all a bit new, maybe a bit scary, so let's try and have a think about what that actually is all about. So the outcome, the stuff on the left hand side of the equation, is the log odds of the outcome occurring. Now I'm going to spend a bit of time talking about what the odds are, and then hopefully that will make more sense, but these are the odds expressed as in natural logarithms. So it's the odds of the outcome occurring but expressed in natural logarithms, which is not that helpful because most people don't find it that easy to think in terms of natural logarithms. I certainly do not. You know, there are some people who do, but I'm not one of them. You know, natural logs do not come easy to most of us mere mortals, but we can take comfort from the fact that, as I said, on the left hand side we've got lots of things that seem familiar. So for example, we've got a beta 0 that we're going to estimate, we've got a beta 1 that we're going to estimate, and you know, that the part on the right hand side is the same as all the models we've looked at before. So for example, the beta 1, it still represents the change in the outcome from a unit change in the predictor. It still represents exactly the same thing. All that's different is that the outcome is now the log odds of the outcome occurring rather than being the outcome itself. So beta 1 now represents the change in the log odds of the outcome associated with the unit change in the predictor. Now here, the predictor can either be Christmas pudding or mince pie. So the beta 1 is going to represent the change in the log odds as we log odds of the outcome as we go from eating Christmas pudding to eating mulled wine. The beta 0 also represents the same thing as in a kind of ordinary general linear model. It is the log odds of the outcome occurring when all the predictors are 0. And in this case, when treat is 0, that was the Christmas pudding condition, I think, if I've remembered correctly. So the beta 0 would represent the log odds of the outcome occurring when Christmas pudding is the treat. So lots of stuff that's familiar and the same as before, but something that's very kind of different, which is that the outcome is now expressed in the log odds of the outcome occurring. This is helpful in what we're going to come to in a minute. It's just a reminder of some maths, and it's a reminder of the relationship between the natural log and the exponent of a variable. And this is just to remind you that one kind of reverses the other. So if you take the value 1, the number 1, and you take the natural logarithm of the value 1, you get 0. So if your input to the natural log is the value 1, your output from the natural log is a 0. If you take that output and take the exponent of it, so if you take the exponent of 0, the outcome of that is 1. So the exponent converts a logarithm kind of back to its kind of original value. So if you take the natural log of 1, you get 0. If you take the exponent of 0, you get back round to 1. So this is just to remind, or maybe you never knew this in the first place, I don't know, but it's just to remind you that exponents, because we're going to talk about exponents quite a lot, exponents convert logs back into kind of non-log units. So it's a way to get something expressed as a natural logarithm and convert it back into something that we can kind of make sense of. We had a look a minute ago at the equation, and we saw that we had a beta 0 that represented the log odds of the outcome when the predictors are 0. So in this case, when treat is 0, what are the log odds of delivery? Now, because no one really likes, there are probably some people who do, right? But most people don't like thinking about logs. We can convert this back to sort of non-log units by using the exponent. So as I just explained, the exponent is a way of kind of getting things expressed as logs back to sort of original units of measurement. So if we take the exponent of b, what we end up with is the odds of the outcome instead of the log odds. And the odds of the outcome are the odds after a unit change, well, for beta 1 it would be the odds after a unit change in the predictor divided by the original odds. So it's just expressing the outcome in terms of odds instead of log odds. So when we look at beta 0, for example, it's easier to interpret the exponent of beta 0 rather than beta 0 itself, because that will be the odds of the outcome when the predictor is 0. And for our beta 1, the beta attached to treat, as in the big equation at the top of the slide, this represents the change in the log odds of the outcome associated with the unit change in the predictor, but it again is easier to interpret the exponent of that value. So rather than interpreting b directly, it's easier to interpret the exponent of b, which gives us the log odds associated, gives us the odds of the odds ratio associated with the unit change in the predictor. So it's the odds after the predictor is changed by a unit relative to the original odds. So this odds ratio that you get, we can interpret that with reference to 1. So the value 1 would mean that the odds ratio basically hasn't changed. A value greater than 1 means that as the predictor goes up, the probability of the outcome occurring also goes up. So the odds ratio represents the fact that a unit change in the predictor is associated with an increased probability of the outcome occurring. If the odds ratio is less than 1, then it means that as the predictor increases, the probability of the outcome occurring decreases. So the outcome is becoming less probable as the predictor increases. So typically we would interpret the odds ratio. So let's have a look at what odds are. Here we have a classification table of deliveries and non-deliveries based on what treat our elves had. So when they had Christmas pudding, there were a total of 178 elves who had Christmas pudding as their treat. 150 delivered their presents, 28 did not deliver their presents. We had 220 who had mulled wine as their treat. 100 of those delivered their presents and 122 did not deliver their presents. And you can look in total, we had 250 successful deliveries, 150 non-successful deliveries, and in total we've got 400 cases of data. So let's have a look at what odds represent. You hear about odds all the time, as you go around the world, like if you're into sport, whatever, you often hear about the odds of a team winning or the odds of someone winning a race or something like that. We're surrounded by odds. If you read the news, people are always talking about the odds of things happening and stuff like that. So what are the odds? Well, let's look first of all at the odds of delivery. So the odds of something, I really feel like I'm saying the word odds a lot. Odds. The odds of delivery are the number of things delivered divided by the number of things not delivered, or the number of deliveries divided by the number of non-deliveries. So odds are just kind of the number of things that happen against the number of the same things that didn't happen, basically. So if we look at the odds of delivery, how many deliveries were made? 250. We divide that by how many deliveries were not made? 150. So the odds of delivery were 1.67. That means it was kind of 1.67 more deliveries, 1.67 times more deliveries than there were non-deliveries. In other words, it was more probable that you would get your presents delivered than not. And hopefully you can see where this kind of cutoff for the odds ratio of 1 comes in, because if this number and this number are the same, you'd get an odds of 1, which means the same number of things happened as didn't happen. The same number of deliveries happened as deliveries didn't happen, which of course means it's as likely that you'd get a delivery as not. So let's look at some other odds. So what about if we look now at the odds of delivery after pudding was eaten as a treat? So this again is like, it's the number of successes divided by the number of failures, the number of things, number of deliveries that were successful versus the number of deliveries that were not after pudding. So going back to our table, we're just looking at this row here now. So when they had Christmas pudding, there were 150 successful deliveries, 28 unsuccessful deliveries. And they're the values that are on this slide. So 150 successful deliveries versus 28 non-successful. We get an odds of 5.36. So that means 5.36 times more deliveries were successful after Christmas pudding than were unsuccessful. So you're much more likely to get a delivery than not after Christmas pudding was eaten. What about if we look after wine? So now we're looking at the odds after wine was used as a treat. Again, we can skip back to this slide. And so now we're just interested in this row. So after wine, there were 100 successful deliveries and 122 unsuccessful ones. So how does that kind of pan out? We plug those numbers in and we end up with a value of 0.82. So after drinking wine, 100 deliveries were successful, 122 were not successful, so we get a value of 0.82. The fact this is less than 1 tells us that there were more unsuccessful deliveries than successful ones. So in other words, if you leave out mulled wine as a treat, you are the probability of getting your presents is lower than the probability of not getting your presents. So in other words, if you want some presents for Christmas, maybe don't leave out the mulled wine. Now the odds ratio, this thing that I mentioned a couple of slides ago, is the ratio of those two odds. So it's the odds of delivery after wine divided by the odds of delivery after pudding. So we take that value, we know the odds of delivery after wine was 0.82, we divide it by the odds of delivery after pudding, 5.36, and we get a value of 0.15. So that tells us that the odds of delivery after wine were quite a bit smaller than the odds of delivery after pudding. So in other words, the effect of kind of leaving out wine relative to pudding was that the odds are much smaller. The odds of delivery are much, much smaller than they are for pudding. Again, the fact this value is less than 1, if it was 1, it would tell you that the odds of delivery after wine were the same as the odds of delivery after pudding. And if it was greater than 1, it would tell you that the odds of delivery after wine were more than the odds of delivery after pudding. And you can express this either way round. So I've expressed it this way round, but this slide is just to show you we could flip it. So we could look at the odds of delivery after pudding relative to the odds of delivery after wine, and we would just get the reciprocal. We flip the fraction and we get a value of 6.54. So whereas the previous one told us the odds of delivery after wine were much smaller than after pudding, this is telling us the same thing but phrased the opposite way around. The odds of delivery after pudding were much higher, so it was 6.54 times higher than the odds of delivery after wine. So in other words, much more likely to get a successful delivery if you leave out pudding relative to wine. Okay, so let's fit the model. And we can fit it in R so we've been using the LM function a lot throughout term. We now use the GLM function, but it's basically the same. So we express the formula in the same way. So we're predicting the variable delivered from the variable treat. We tell it where our data is. The only difference is we add what's known as a link function. So this family equals binomial is just is telling the function what link function to use. And in particular, this is a link function that makes everything kind of logarithmic. That's a really bad way to explain it. But anyway, it's the thing that sort of turns LM into something that can deal with categorical outcomes. There you go. So we fit the model kind of in a really similar way to before. It's just we're, like I said, express it. We have to put in a link function. And we can take our object and we can put it into the parameters function to get a nice little summary table that's nicely formatted. And nice little tip as well is if you want APA style p-values, you can if you pipe your parameters table into a function called parameters table and specify you can specify how many decimal places you want on your p-values. You'll get something, you'll get these things formatted at the end. Right, so what do we have here? Well, essentially we've got a table very, very similar to what you've seen for other linear models. So we've got an effective treat. This is telling us it's mulled wine versus Christmas pudding. We've got a coefficient, we've got a beta. So that's beta 1, this is beta 0. So this beta 1 is the log odds of delivery after mulled wine relative to after pudding. This is the confidence interval for it, a significance test, which is highly significant. So treat's a highly significant predictor. But how do we interpret this minus 1.88 log odds? Like it's hard because, you know, no one wants to think in logs. So like I said, a lot of the time we would convert these betas into we'd use the exponent of b instead of b, which gives us a nice odds ratio. And we do this, I've just highlighted the bit of code that would be different. So when we put it through parameters, we just set this argument exponentiate equals true, and all that does is it converts, it takes the exponent of all the values. So we now get this, the effect of mulled wine versus Christmas pudding expressed as an odds ratio. Rather than being log odds, it's now an odds ratio. So it's been converted back into non-log units. The significance test is exactly the same. We're just re-expressing the betas. The confidence interval has obviously changed because we're converting the betas into a different unit of measurement. But essentially this is our beta 0. So this is the odds of delivery in the Christmas pudding group, 5.36. And if we scroll back to here, that was the value we calculated right there. And our odds ratio is 0.15. So this is telling us that the odds of delivery after mulled wine are 0.15 times the odds of delivery after Christmas pudding. And again, we can skip back a few slides and see that that's the value we calculated there. So basically what this model is telling us is that treat does predict the odds of delivery. And in particular, if mulled wine was the treat, then delivery was, the odds of delivery were much smaller, really a lot smaller than if Christmas pudding was left as a treat. So the kind of, the message here for Santa is keep the elves off the mulled wine.
Well, Eddie, I've got some bad news, I'm afraid. The problem seems to be the mulled wine. I think this year I'm going to have to forbid the elves from partaking of the mulled wine.
Oh dear, I don't think the elves are going to like that. Santa, bad news, bad news! I fed your report back to the elves and they're not happy. They're saying they won't deliver the presents if they can't have mulled wine.
Oh dear, but Santa needs the elves. I can't deliver all the presents by myself.
They say it's not the mulled wine that's the problem, it's just that they drink too much. Even if they were allowed a small amount of mulled wine, it would help to see them through the busy night of Christmas Eve. Can't they have just a little bit?
Oh, well, okay. I'll see what I can do.
Oh dear. Oh, as if that wasn't hard enough. We've now got a rebellion on our hands. Well, what can we do about this? So basically, we need to kind of make the model slightly more complicated. So we've had a look at treat. Now let's have a look at the quantity of treat that they consume, because elves deliver over, you know, they don't just deliver at one house, they deliver over lots of houses. So let's see if we can get some data that actually, as well as manipulating treat, so as well as making sure that we know which treat the elves had, we also know how many they had when they visited the house. And again, our outcome's still going to be whether the presents got delivered or not. So we're just kind of adding a predictor here. So here we are, we have our data again. It's actually the same data as before, we've just got a new variable added that we delved up from the database that Santa has, which is the quantity of treats. So we ignored this variable before, and now we're going to factor it in. So Fankel, the determined, had 4 glasses of mulled wine, and rather unsurprisingly, did not deliver his presents after that. Whereas, for example, Ainsley the eigenvector, an upstanding member of the elf community, although tempted with mulled wine in the house that he attended, he didn't drink it. He had zero quantity, and therefore was able to successfully deliver his presents. So what we're interested in now is there an effect of quantity and treat, or do they have a combined effect even? So we can extend the model. We saw with linear models, we've done this all through term, that you can extend linear models in a very kind of straightforward way by adding in new predictors, giving them a parameter that we then estimate from the data. And in this kind of design where we're maybe expecting the type of treat to moderate the effect that quantity has, we could put in an interaction term as well. Now all these things still apply. Just because the form of the model has changed, we can still basically just extend it in the same way. But remember, now we're dealing, or one way of thinking about it is dealing with the probability of delivery, but we can still just extend the model in the same way. So before, this model only had treat as a predictor. We're now added in quantity. We've added the interaction of treat and quantity. We've assigned them a parameter that we're going to estimate, and so on and so forth. But the basic model stayed the same. We've just expanded the linear part of it. Or indeed, we can express it as log odds on the left-hand side. And then the right-hand side looks very, very much like the kinds of models that we've been fitting all terms. So we've got effective treat, effective quantity, and the interaction between the two. Bearing in mind, quantity is a vaguely continuous predictor. So we're not treating that as categories. We're treating that as a continuous predictor, like 0, 1, 2, 3, 4. Treat is still categorical, Christmas pudding or mulled wine. And we're coding that in the same way, Christmas pudding being our 0 category. The point of this slide is really just to point out that even though we're adding predictors, and even though we've got this kind of slightly different outcome in that we're predicting whether things get delivered or not, the way the model expands is the same as all the models we've looked at all term. Okay, now when you've got multiple predictors, you can build the model in the same way as other linear models that we've looked at. We can use forced entry, just put all the predictors in at once. The ideal scenario is to do things hierarchically, so you enter variables in blocks based on kind of past research or theory being tested, etc, etc, etc. In our case, it's more forced entry makes sense because we want to look at the interaction, so we therefore got to have the main effects in the model anyway. There is also the option to do stepwise variable entry as well, so you have a bunch of variables and you put them in based on a sort of statistical criterion. Had loads of caveats about that earlier in the module, and the same caveats apply. So you really use it for exploratory analysis. Definitely doesn't make sense in this particular analysis because we've got a very clear prediction that the quantity and treats should sort of interact in some kind of way. So things that can go wrong in this kind of model. Well, things we've met before. We still have an assumption of linearity, believe it or not, but because we've used this kind of log transform to kind of reconfigure the model, the assumption is around linearity of the logit, so not linearity of the kind of raw outcome. We've still got issues like spherical residuals and independent residuals, so we wouldn't want to have residuals, for example, from the same participants. There are different types of models we'd need to fit in that case. So in our data, each elf has only contributed one delivery score, not lots and lots of delivery scores. You still need to think about things like multicollinearity in your predictors. But there are also a couple of unique problems that you get with these kinds of models, these kind of logistic models. The first one is incomplete information, and the second one is complete separation, which I'm going to talk about now. So incomplete information is to do with how, when you have categorical outcomes, you end up with sparseness or it's much more likely you'll end up with sparseness in your data. So to give you an example, if you look at the data table here, so what I've got is I've kind of mapped out a sort of a cross tabulation where we've got each value of quantity 0, 1, 2, 3, 4 for pudding and for mulled wine, and then we're looking at how many were delivered and how many were not delivered. And actually, this is believe it or not, a relatively simple kind of model. We've just got two variables. Quantity has 5 different values, which for a continuous variable is not that many. And pudding and mulled wine can only take on 2 values. So across that, we effectively we have 20 cells, right? so that we need filling, so 20 cells that need some data in. The delivered and not delivered columns represent kind of counts, really. So for example, when we look at those that had 0 pudding, so pudding was left out but they didn't eat it, we know there were 27 deliveries and 3 non-deliveries. And bearing in mind we've got 400 cases of data here, so you think it's kind of like quite a big data set. But you can see, I think very quickly from this, first of all, non-deliveries were not that common. All right, so it's not that common that you didn't get non-delivery. So all the values in the not delivered column are quite small, like, you know, you've got 3, 10, 5, 6. So already we don't have a lot of data about non-deliveries really in the grand scheme of things. We've also got some completely missing cells. So for example, in our 400 cases of data, there is no case of data where they had 2 doses of pudding and delivered their presents. Just didn't happen. In actual fact, there just weren't many cases where they had 2 doses of pudding. There were only 5 cases in total, and they were all ended up in being non-deliveries. So we've got a gap in our knowledge there. And the same with mulled wine. When there were 4 doses of mulled wine, we have relatively little information about deliveries and non-deliveries, because hardly anyone drank 4 glasses of mulled wine. Hardly any of the elves did, because I mean, you know, elves are small, so 4 glasses of mulled wine, that's not going to go down well, is it? So, you know, we've got 3 deliveries and then, you know, a blank for non-deliveries. We just don't know. There just weren't any elves really having that much mulled wine. So you get these kind of gaps. We've got a gap here where we just don't know anything about what's happening. We've got a gap here where we just don't know anything about what's happening. And you might think, well, that's only a couple of gaps, isn't it? But this problem really, really starts to escalate very, very quickly, especially if you have, you know, even with quite big data sets, you're going to just start having big gaps in the data. So imagine, for example, that as well as quantity, we took elf experience into account as well. So like how many years they had been elfing. Then you then have another column, and for like pudding and quantity 0, you'd then have like 1 year, 2 year, 3 years, 4 years, 5 years. So you'd have, you know, another like 5 rows for every row in this table. So you'd start getting a kind of huge grid that you needed data for. And you know, I think you can probably quickly imagine that you'd start getting lots and lots of empty sparse cells. So incomplete information is a problem, and it can inflate the standard errors in the model. The second issue is something known as complete separation, and this is when the outcome can be perfectly predicted. So to give you an example of this, I want you to imagine that you, I mean, maybe you knew about the Krampus before. Maybe this lecture is the first time you ever heard about the Krampus, and now you're super, super scared of Krampuses or Krampi or whatever they're called coming to your house and taking you off in a bucket or leaving you with coal. So you're a bit worried about this Krampus situation. So you decide to make yourself a Krampus detecting device. And you put this device, you know, the major entry point for your house, like at the bottom of the chimney, for example, or, you know, however you think they're going to come into your house. And when something lands on it, it measures its weight. And then if it thinks it's a Krampus, it sets off an alarm so that you wake up and can escape. Now imagine a scenario where there are no elves. So Santa's doing all the deliveries. So what's going to come to your house is either a Santa, because, you know, Santa exists in a superpositional state so that he can deliver to multiple places at once. So either it's going to be a Santa coming into your house, or it's going to be a Krampus. Now Santa's weigh anywhere between about, say, 90 kilos, or say 95 kilos, and about 145 kilos. Krampuses in general are slightly heavier. They start off at about 120 and they go up to, yeah, maybe just under 155 kilos. So you can build a model here to predict whether the thing landing on your sensor is a Krampus or a Santa. And you basically, you have a logistic model, and you got your outcome here is probability. So if it weighs, you know, like 150, well, a bit more than that. So if it weighs like 155, the probability of it being a Krampus is 1, because there are no Santas that weigh that much. Whereas if it weighs like just under 100 kilos, probability of being a Krampus is 0. There are no Krampuses. You can see, so these are the Krampus weights up here. So there are no Krampuses that are that light, so you're going to get a probability of 0. And this curve, the red curve, represents the probability curve of being a Krampus. And the midpoint on this curve is where your sensor flips. So basically about 134 kilos or something, if something of like 135 kilos lands on it, the Krampus alarm goes off. And if anything below that, then it doesn't go off. It assumes it's a Santa. Now it's going to be wrong some of the time. Sometimes it's going to say it's a Santa and it turns out to be a Krampus. But that's the curve. That's the curve that your measuring device is working on. And that's basically when we fit a logistic model. That's what we're doing. We're kind of that curve is kind of like related to our outcome. Now what happens though if instead of Santas it's elves that are doing the deliveries? So we've now got a different scenario because all our elves are super light. They're all under 45 kilos, and our Krampuses are still quite heavy. They're like 110 kilos plus, 120 kilos plus. So now you've got this red curve, and you've still got that midpoint of that, about 80 kilos. But you've got what's known as complete separation or perfect prediction. So there's no error in this model at all. If something is bigger than 80 kilos, it is a Krampus. There's no elves that have a weight bigger than 80 kilos. And if it's below 80 kilos, it is an elf. So, there's no error in prediction. And the consequences of that is, although we've got this nice red curve, and you might think, well, that's great, there's no error in prediction. Surely that's what we want. But the problem is, you could fit an infinite number of curves between these points. So you've got this red curve here. That's one curve that fits the data. But you've also got this blue hashed curve, which is another curve that fits the data. And you could have another, they'd all go through that point, but you could have another curve that fits the data. Essentially, you've got an infinite number of curves that fit the data. So an infinite number of kind of models, really, or infinite number of curves of predicted values that fit the data. And basically, that's going to mess up your life in painful and horrible ways.
And now it's time for a Christmas song. Don't you agree, boys and girls? I thought so. Let's get to it. Yeah, it's coming to town. Yeah, it's coming to town. Logistic regression is coming to town. You better watch out, you might want to cry. You better beware, I'm telling you why. Logistic regression is coming to town. Santa's checking the output, he's checking it twice. He's gonna predict who's naughty or nice. Logistic regression is coming to town. He's got a binary outcome, residuals are normal, but with a logic log function, everything is cool. So there's nothing to fear, there's no need to cry. It's like every other model we've tried. Logistic regression is coming to town. The effect of predictors is easy to see. You just need to check the exponent of p. Logistic regression is coming to town. But design cells can be empty. That's incomplete information. And if prediction is perfect, then you have complete separation. But there's nothing to fear, there's no need to cry. It's like every other model we've tried. Logistic regression is coming to town. There's nothing to fear, there's no need to cry. It's like every other model we've tried. Logistic regression is coming to town. Let's have a look at fitting the model. Basically, do something similar to before. So we use GLM. We're still predicting deliveries, but now we're predicting it from treat, quantity, and the treat by quantity interaction, which we can express just as treat asterisk quantity. And again, we pump that into the parameters table to get some nice looking output.
And we end up with this. So again, by default, oh, not by default, I mean, the model's going to pump out betas that are expressed as log odds. So all these values here are log odds of the outcome. And they've all got significance tests and p-values attached to them. So we can see, for example, there's no significant main effect of treat. There's no significant main effect of quantity, but there is a highly significant interaction. So it does look like the effect of quantity is moderated by the treat that you have. Now we've got this log odds for the interaction term, and I just want to kind of explain what that represents. So its value is minus 1.03. Now where does that come from? Let's imagine for a moment that we just looked at the effect of quantity, but only for Christmas puddings. So what we're doing, we're taking our data, we're filtering it, so we're only looking at when treat was equal to pudding, and then we're fitting a simpler model that just looks at delivery predicted from the quantity of treats eaten. And we get out this table, and the log odds of delivery for the variable quantity are minus 0.08. Let's do that same exercise, but now we're going to filter for mulled wine. So we're only looking at the elves in the data that had mulled wine. Again, we're fitting exactly the same model, so delivery based on quantity. And the log odds of delivery based on quantity when mulled wine was drunk is minus 1.11. Let's compare these two values. So what happens if we take the beta for the mulled wine condition, or for the mulled wine elves, and we subtract from it the beta for the elves that had puddings? So what we're basically doing, we're taking this value and we're subtracting from it this value. So this is going to tell us the difference in the effect of quantity between the mulled wine and the Christmas pudding. And when you do that subtraction, you end up with a value of minus 1.03, which was the log odds for the interaction. So the interaction term is telling us the difference in the log odds when Christmas pudding was the treat relative to when mulled wine was the treat for the predictor quantity. As I've said a few times, easier to think about this when expressed as an odds ratio. So we can put this into the parameters function and get it to calculate the exponents for us. Again, just a reminder, the z's and p-values haven't changed, but now for the effect of the interaction we get an odds ratio and the associated confidence interval for that odds ratio. So the odds ratio for the effect of quantity in mulled wine relative to when Christmas pudding was the treat is 0.36. So it's a positive value, and basically if we go through this exercise again, and you remember that the log odds for the difference in the effect of quantity when mulled wine was the treat compared to when Christmas pudding was the treat was this value of minus 1.03. If you exponentiate that value, if you take the exponent of that b, so if you take the exponent of minus 1.03, you get 0.36. So that odds ratio of 0.36 represents the same thing. It's the difference in the odds ratio for the variable quantity in the mulled wine group relative to the Christmas pudding group. So it's telling you about how the odds ratio changes, the odds ratio for quantity changes as a function of whether they had mulled wine or Christmas pudding. Now, how do we interpret this? Well, it's quite difficult to think about in a way. One way to do it is to kind of go back and sort of reconstruct the odds in the various conditions. This, I think, is a reasonably useful way to look at these particular data. So I've just converted everything into the percentage of presents delivered. So 100% means everyone in those conditions got their successfully delivered their presents, and 0% means everyone in those conditions didn't deliver their presents. So what we see, for example, we got a line here representing the Christmas pudding group and a line here representing the mulled wine group, and these are the log odds of delivery based on quantity as a predictor. And these lines don't map, that's not the gradient of that line, by the way, so don't think that it is. I'm just reminding you of what the kind of effect is. So when the treat was Christmas pudding, basically this line up here is very flat, and we also get a log odds that's very close to 0. So there's not much change essentially in the log odds as quantity changes. So the line's very flat. So the percentage of presents delivered stays pretty constant regardless of how much is eaten when the treat is Christmas pudding. Contrast this with when the treat is mulled wine, and you can see you get a kind of steep decline in the number of presents delivered as a function of how many treats are eaten or consumed, and that's reflected by the bigger in magnitude, more negative log odds that was associated with that effect. And the interaction is really telling us that these lines kind of diverge. So for 0 treats, as you'd expect, the same proportion of deliveries, about 90% of deliveries are successful. When 1 treat is eaten, there's a really, really small difference between the successful deliveries after pudding and mulled wine. But at 2 treats, this kind of happens. The lines start to really diverge, and you get like a sudden drop in the percentage delivered in the mulled wine condition. So when mulled wine is left out, you get a rapid decline in the number of successful deliveries at 2 treats, or when 2 of them are eaten, and that continues. It goes down even further after 3 treats, and actually the difference here is probably about the same for 4 treats. But anyway, it's basically you get a kind of rapid decline in the presents delivered as more mulled wine is consumed, but when Christmas pudding is consumed, it stays relatively flat. So it looks as though it's okay for the elves to eat Christmas pudding. They can have, as much of that as they like. Well, at least up to 4 treats, which is what we measured. But it's not okay for elves to drink more than 1 glass of mulled wine. If they have 2 or more glasses, then basically it all goes a bit pear-shaped. But the good news is they can have a glass. They can have 1 glass, and that's fine, but just not 2 or more.
And so it was, boys and girls, that I was able to report back to the elves that they could in fact have a glass of mulled wine when they deliver the presents, and they were very excited and very happy and agreed to deliver the presents, and Christmas was saved. Now, of course, I haven't forgotten my promise, I said that if Christmas was saved, then I would release you from the hell of this module so that you can have a lovely winter vacation. And so I will. With a magic sprinkle of Christmas fairy dust, you are released and free to enjoy whatever you do at this time of year. Tally-ho! Ho, 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 ho! Now for a festive tune from my favourite Christmas band. It's Wizard, of course!
When the snowman brings the snow, well, he just might like to know.
It puts a great big smile on somebody's face.
If you jump into your bed,
Quickly cover up your head.
don't you lock the doors, the sweet Santa Claus is on his way.
Well, I wish it could be Christmas every day. When the kids start singing and the band begins to play.
Oh, I wish it could be Christmas every day. Let the bells ring out for Christmas. When we're skating in the park, if the storm cloud paints it dark,
Then your rosy cheeks gonna light my merry way. Well, the frosticles appear, and they're frozen up my beer.
So we'll lie by the fire till the sleep simply melts them all away.
Well, I wish it could be Christmas every day. kids start singing and the band begins to play. Oh, I wish it could be Christmas every day. So let the bells